Hello everyone, my name is Anthony Shivkumar, and in today's video we're going to have a series on brushless DC motor. In this video series, it's going to be a small little playlist where I really want to talk about how we can control a brushless DC motor. Now what I'm currently using is off-the-shelf, brushless DC electronic speed controller in order for me to control this motor. But what I really want to do in this video series is actually make our own electronic speed controller. These are called ESCs, and how we're going to make them. Now this is very complicated, but we'll try to break it down, try to program a microcontroller and try to control a motor using our own hardware. So before I get started, what exactly is a brushless DC motor and why is it difficult to control? Why can't I just put two wires and make it work? As you can see, there are three wires to control this brushless DC motor. And why do we need three wires? And if we're controlling this motor, why is this more difficult than, say, a normal DC motor, which has brushes? And what makes this more sophisticated, much more complicated to control? As you can see, if I connect this to my Arduino, connect to my wireless radio channel over here, I can control this motor. So let's break down and see what exactly is in this ESC. So if I tear apart one of my ESCs, which I have over here, and I ripped it apart, I have the electronic speed controller. Now this is some sophisticated electronics in here. At least it's not, you can't just look at it and say, I understand this. It's got, a couple of MOSFETs in here. It's got three wires which are supposed to be connected to this motor. I have cut them off. The reason why this is not particularly working, which I could probably repair, is because the capacitor blew off, and I just thought it would be a good idea to look what's inside the brushless DC motor speed controller, because we're going to make one in this particular video series. All right. So as you can see over here, they have 6 MOSFETs, and this is what we call as an H-bridge configuration. I'm going to show you a schematic to show you exactly why we need this. And this allows us to basically control the magnets, to activate certain magnets in this motor so that it starts to spin in a particular direction. So that's what these MOSFETs do. So each time a MOSFET is activated in pairs, so you have pole pairs because there's always north and south. So that's the reason why you have the high side MOSFETs and the low side MOSFETs. We'll discuss more about the schematic as to what this really means. It activates a magnet. The magnet basically forces the motor to align. So on the rotor side, we have permanent magnets, and on the stator side, which is the stationary side of it, we have the electromagnets. So these MOSFETs are activating the electromagnets inside this brushless DC motor, and each time they're activated, they spin and align the permanent magnets to it. And if you do it fast enough, it starts to create a rotational motion. So how does it know which magnets to activate? Because you could activate any magnet and it could start to stall. How does it know how to activate these magnets in a very specific way so that it rotates in a smooth way? That's something known as back EMF, and back EMF allows us to understand where the position of the rotor is, so that we know which two magnets to activate next, or which two MOSFETs to trigger so that it activates the magnets, the electromagnets, that then align the permanent magnets. That's really what's happening in a nutshell. So that's why it's a complicated circuitry to control this brushless DC motor, and you have to use electronics to do this, or else you won't make this work. So let's look at a schematic as to how we're going to basically design this particular motor, or this particular electronic speed controller. In this video series, I'm specifically going to design one from the grounds up. We're going to fabricate one, and we're going to write software to control it, so that we really understand what these brushless DC motors, how these speed controllers work, and how you can apply them not just to brushless DC motors, but even to permanent magnet synchronous motors and all the different types of various motors that requires some form of electronic commutation in order for us to rotate the motor. Commutation basically means rotation, just in a nutshell. You're activating the electromagnets to basically rotate. So what is the process of basically making this motor rotate? So let's get started. So in here, I have my electronic speed controller circuitry, and what we have over here is designing a pre-driver. So as I mentioned, that this particular brushless DC motor has a microcontroller in here that is basically activating these MOSFETs. And in my circuitry, what I'm trying to do over here is I'm going to basically use a pre-driver, which will be connected to a microcontroller in order for us to activate these MOSFETs. So these are the MOSFETs, these are the H-bridge MOSFETs. And I've already fabricated this particular board. So this is what this board over here that you see on the screen is over here. So this is the brushless DC motor, and I'm trying to basically write the software right now in order to activate and control this motor. And these are my 6 MOSFETs, very synonymous to what we have over here. The 6 MOSFETs on this brushless DC motor, which is basically, this is the hobby version of the brushless DC speed controller. And this is my version, which I basically designed over here. And the way it works is we have these 3 little outputs. So these are the outputs of the motor, these 3 little knobs. And these 3 knobs is very similar to what we have over here, the 3 things. And this is basically will be connected to each motor over here. And each time we activate different MOSFETs, it'll basically activate this particular motor. But there's also one thing to recognize over here is each time I actually rotate this, and I'm going to basically use my oscilloscope to show you what I mean. So each time I rotate the motor over here, you can really see that my oscilloscope starts to, show that there are ripples, and then it stops. So each time I rotate, it stops. Each time I rotate, it stops. The waves get bigger, and then when I stop, it stops. So what are these waves? What is this that it's doing? So generally, every motor, as much as I can control the electrical side of it to produce the mechanical output, I can also, vice versa, as I rotate it from the mechanical side, I can generate electricity. So in one way, it's called a motor, and then the other way, it's called a generator. And this generating action, which is basically called back EMF, is how we can identify the position of the stator or of the rotor, basically. So every time I'm moving, it is, and I've just basically connected to one of the knobs over here, the oscilloscope. So if I connect to all 3, it'll tell me where exactly is the stator aligned, and based on what the where the rotor is, each one will be activated accordingly. That means electricity is going to be, or the back EMF is going to basically come from one of these phases. So each one of these are called phases: phase A, phase B, phase C. So this is what we're going to use as a way in order for understanding the position of the rotor, in order for us to activate the MOSFETs so that we can generate and activate the right electromagnets for creating rotation. Because as it is rotating, it is also creating a back EMF. So this phenomena allows us to basically control the MOSFET. This is for a sensorless brushless DC motor, and for a censored brushless DC motor, you would probably have an all-effect sensor, and you don't necessarily need to use a back EMF. You could just basically, use the all-effect sensor to know the position. But in this case, we want to keep our circuitry minimum. We want to keep our cost minimum. So we're going to use the basic, the phenomena of physics for us to understand where the position is. Because without position, we wouldn't know what MOSFETs to trigger. What does this particular circuitry do? So as I zoom in, it doesn't matter whether you have a pre-driver or whether you don't have a pre-driver. You will still need to have 6 MOSFETs, or at least a way to activate the electromagnets that are there in your motor. So in this particular case, what we have over here is we would have our MOSFET 1, MOSFET 2, MOSFET 3, MOSFET 4, MOSFET 5, MOSFET 6. So whenever you get a back EMF, say from phase A, that means you kind of know that the position of the motor is somewhere between, that means we know the position of the motor is between phase B and phase C. That means that's where the rotor is. And then we activate those motors, those MOSFETs, to get the to get the back EMF on the other phase. So at any given time, only 2 phases are activated. So every time in a motor, every time I move, only 2 phases are activated and the 3rd phase will be generating. So that's how this back EMF basically works. I will do a lot more detailed simulation as to how this works, and to really get an understanding of how this back EMF actually works. But in this particular video, I just wanted to showcase what we're designing before I go more into the details as to how we can make this all work. So in here, I've got my circuitry. I've already designed this, as I mentioned. This is what it would look like, and this is what we have over here right now. It's a fabricated board. It's exactly what we have over here. And I mean, with all the thing, it looks exactly what it looks like. And why do we have so many wires over here? Why do we have so many outputs in here? So let's have a look at what we're really controlling, because this is important. This is important to know, how does a microcontroller actually connect this? So leave alone this chip for now. This is just a pre-driver. Think of it as a protection unit between, say, the delicate microcontroller and the high power MOSFETs. And this is just a buffer. Just think of it that way. So they call it a pre-driver. So if you really look at it, what we have over here, we have a couple of inputs to this particular pre-driver, which is basically going to control the motor. So what do we need in order for us to control the motor? So my microcontroller needs to technically have 6 outputs. So the 6 outputs is to control the 6 MOSFETs. And how does a MOSFET work? You basically can turn it on or you can turn it off. So based on what MOSFETs do you want to turn on? What MOSFETs do you want to turn off to activate certain electromagnets? So those are the 6 motors, 6 pins over here. So that's PA is phase A high side, phase B high side, phase C high side, and that's phase A high side, phase B high side, and phase C high side, and then we have the low side. I'll do a detailed simulation in another video. It will be beyond the scope of this particular video, and we'll go into detailed understanding as to how each phase is activated, and how voltage and current flows through each MOSFET, and how it should flow, and what are the possible problems that you can face if you don't activate the right MOSFETs in the right manner. You can cause a big short circuit and probably destroy the board, because there'll be a huge current flowing through it. So those are the things I will discuss in another video. But just in this particular video, I'm just really focusing on, what are the things that we really need to control this motor? Like, what are the inputs to control these H-bridge MOSFETs? Okay. Then what we have over here is the SPI protocol, in order for us to communicate with the pre-driver to understand, what's certain parameters, make sure that there's no error, make sure that the voltage is not over voltage, or there's too much current. So the MOSFET, so the pre-driver can can do some protection against the circuit. And if there's something that's wrong, we can basically communicate with the pre-driver in order for us to understand what's going wrong. So think of this as just an SPI communication between the microprocessor and the pre-driver. And here we have the back EMFs. The back EMFs will now be connected to the analog and digital converter of our microcontroller. And the back EMF is exactly what I spoke about a little earlier, is that each time we move, each phase will be activated based on, each phase will create a back EMF based on the position and of the rotor. And that voltage is important for us to sense the position of the rotor. And from that position, we can then basically activate the correct MOSFETs using these 6 MOSFETs over here, signals to the MOSFET. So the back EMF tells us the position. We take that position, make sense of it, and then activate the right MOSFETs. And accordingly, we do this, around like 20 kilohertz is the general frequency. So we're doing this, 20,000 times a second to make sense of it. That's that's a lot of, that's very high speed. And a microcontroller can do that. We're not dealing with 1 second and 2 seconds. We're dealing with, in kilohertz. And this is the reset and enable for the pre-driver. All right. And then we also have these 3 inputs again that will be fed into the microcontroller. And this is the overcurrent output. This is the current, the amount of current flowing to the whole device, and if there's any interrupts by the pre-driver. So in a nutshell, if I have to use my microcontroller, in this case, I'm using my KB5X. I can also use my LPC1769, doesn't matter. But my microcontroller needs to connect to the pre-driver for protection, and then these 3 outputs will be connected to a brushless DC motor. So what are the pins that I need to activate in my microcontroller in order for me to control this? Because I'm trying to use one microcontroller to control at least a couple of brushless DC motors. In here, we have one isolated, the manufacturer over here, the hobby kit over here, basically supplies this whole ESC under one package. In my use case, I'm not particularly going to do that. I'm going to use this as a flight controller and a motor controller in one particular IC. But that might be a little bit more complicated. We're not going to go more into details of that. But my goal is to at least write the algorithm that would work across most microcontrollers. And that's what this is really all about, which is basically figuring out the position, calculating the back EMF, then activating the right MOSFETs, and then from there, creating the rotation, and then also adjusting the voltage based on pulse width modulation. So because based on the voltage, we can control the speed of the motor. So all this cool stuff is basically part of this video series. This is just the intro, and I just wanted to show you what to expect. It might be a little bit too dry, but I just wanted to show you, how the whole progress will be in order for me to act. I'm probably going to waste, spend at least another 1.5 months to 2 months to do this. I'm not going to lie about this. This is not necessarily easy. This is actually very difficult to implement by yourself. When you buy these hobby kits, it's so easy to just, buy this and make this work. But to break your own is very, very complicated. It's not easy, especially when you're making a custom built solution. But that's where's the fun if you don't build your own custom solution. And especially if you're creating drones that you want to have very high flight stability, high control stability, you need to understand how you're controlling the motor, because the motor is going to control the drone. So if you don't know how this whole system works, I think it doesn't make sense for you to basically create a great control algorithm without understanding. You don't necessarily have to create your own, but at least understanding how this works can really make a whole huge difference. Because then you can focus on how much power this is consuming, what are the voltage limits, how is the speed, how can I make this more efficient. With that feedback, can I add that feedback in order for me to control the speed of the motor more precisely? How precise is this? We don't know. I mean, yeah, sure, it's spinning, but how precise is it? Is it precise enough for me to do much more complex control algorithms onto it? What are the feedbacks I'm getting from this? And all those things you can add with your custom built solution. Whereas with a pre-built solution, you might probably have to customize it a little bit to a point where you might as well make your own electronic speed controller. So that's what this video is all about. And in the next video, I will try to start to program this microcontroller and also explain to you how each phase of the motor actually works. And there's also a lot of YouTube videos that show you how to do this. So I don't really want to add to really a brilliant pool of knowledge based on how brushless DC motors work. But there's not a lot of videos that show you literally how do you program the microcontroller to make this work, at least at the detail level. And that's what I'm really trying to build over here. This is a vlog series, so that's the reason why it's important for me to show you my progress. As I mentioned, it'll take around 1.5 months to 2 months to figure this out and make this work. So one might say, oh yeah, it'll take me a week to do it. Let's see. All right. I don't think it's a week's worth of progress. It's a complicated software to control this. Alright, that's all there is for it. If you like this video series and you want to know more about how I'm building it and you want to learn more as to how you can program your own microcontroller to control a brushless DC motor, please subscribe. Do like this video because there'll be so many cool stuff that I'm trying to work, not just with brushless DC motor. I'm also planning to do a video series on how to control stepper motors. This is a stepper motor. How do you control this? I also have I've basically taken apart my blender. And I've basically taken the induction motor, and then we'll talk a little bit more about how to control induction motors. And in here I have basically I've basically broken apart this grinder or this blender, and I'm taking the induction motor, or maybe I don't know what exactly this motor is, but I think it's an induction motor, and we're going to control this as well. So this video series is going to be, at least my channel will have a lot of these breaking apart these motors that is there in common devices to understand how it works, and then creating a controller to control these things. So if that's something that you're interested in, do subscribe. I think it's real fun making these things work, and also understanding and hacking and to figure out how these common devices that we use is actually very sophisticated, very complicated. And once you get them working, it's quite a joy to really understand how all these things work. All right, and until next time, thank you so much. And stay safe.